I want you to picture a specific moment. You're playing a massive open world game. Maybe it's Skyrim or, The
Oh
Sims.
yeah, total time sink.
Right, exactly. You've spent hours building a house or slaying dragons, and you are totally immersed in this world. And then you decide to talk to a villager.
And we all know how that goes.
You walk up to the local shopkeeper expecting a conversation, and they just look you dead in the eye and say the exact same line they said yesterday.
Need something.
Yes. Or they just walk repeatedly into a brick wall because their pathfinding glitched out. And in that split second, the magic just dies.
It completely breaks the illusion.
You realize you aren't looking at a person. You're looking at a looping animation triggered by a proximity sensor. It's essentially a vending machine disguised as a human.
That's the uncanny valley of behavior right there. In computer science terms, those characters are just finite state machines.
Right.
They follow a very simple logic tree. If the player is at the specific X and Y coordinates, play animation Y. There is no ghost in the machine.
They're hollow.
Completely. They don't remember that you were rude to them last week, and they certainly don't care about your dragon-slaying achievements unless a specific line of code explicitly tells them to care.
But that era of, dumb NPCs might be ending a lot faster than we thought. I've been reading this paper that dropped from a team at Stanford and Google.
Wow, the generative agents paper.
Yeah, it's titled Generative Agents, Interactive Simulacra of Human Behavior. And honestly, reading through it, it feels less like computer science and more like they accidentally invented a digital society.
It really is a massive leap forward. I mean, they didn't just build a better chatbot. They built a functioning, breathing town called Smallville.
A whole town.
Yeah, it's a visual sandbox, kind of like a classic 16-bit RPG game, but it's populated by 25 autonomous agents. And when we say autonomous, we do not mean they just wander around randomly bumping into things.
Right, they have lives.
Exactly. These agents wake up, they cook breakfast, they go to work, form opinions, they gossip about their neighbors, they even plan parties.
And the kicker here, and this is what we're really diving into today, is there's no human puppeteer. Nobody is typing in, "Go to work now."
They're doing it because they actually want to.
So the mission for this deep dive is to figure out how on earth this actually works. How do you take a large language model, the text generator behind things like ChatGPT, and turn it into a guy named John Lynn who runs a pharmacy and, worries about his son's music career?
It's entirely a question of architecture.
Yeah.
The paper is fascinating because it moves way beyond just asking an AI model a question and getting an answer.
It's not just a prompt box.
No, it creates an entire cognitive infrastructure around the language model. It gives it memory, reflection, and the ability to plan. The researchers call it creating believable proxies for human behavior.
Let's start with the setup. We're in Smallville. Who actually lives here? Give us the lay of the land.
So it's a fully fleshed out community. You mentioned John Lynn, the pharmacist. You also have his wife, May, who is a college professor.
Yeah.
You have their son, Eddie, who is a music student. Then there's the Rodriguez family, the Moore family. And each of these 25 agents starts with just a single paragraph of text.
Like a character sheet.
Exactly like a character sheet. A seed biography that describes their job, their relationships, and their basic personality traits.
Okay, so John Lynn knows he's a pharmacist. In a traditional game, that just means he stands behind a wooden counter from 9 to 5. How is Smallville different?
Well, in a traditional game, if you set the stove on fire while John is cooking, he'd probably just keep stirring his empty pot until the on-fire animation triggered.
Right, he doesn't actually see the fire.
But in Smallville, the environment is fully interactive and the agents perceive it. If you, as the user, intervene and set the stove to burning, John actually perceives that state change.
He notices.
He stops what he's doing, he panics, turns off the stove, and this is the really key part, he realizes his breakfast is ruined.
Oh, wow.
So he dynamically replans his morning on the fly. He decides he has to find food elsewhere or he's just going to go hungry.
So he improvises based on the situation.
He improvises based on his current state and his memory. And that brings us to the absolute core engineering problem the researchers had to solve here. We know that large language models have a context window.
Right, there's short-term memory limit.
Exactly. You can only feed them so much text at once before they start to get confused, or, frankly, it just becomes incredibly expensive to compute.
Yeah, if John Lynn has been alive in the simulation for a week, he has thousands of distinct memories. I woke up, I saw the cat, I brush my teeth, I look at the price of eggs.
You can't paste an entire novel into the prompt every single time he needs to decide which shoe to tie first.
It's an information overload problem.
Precisely. So to solve this, the researchers built what they call a memory stream. You can think of it as a comprehensive database log of every single thing the agent has ever perceived or done.
Just a giant spreadsheet of thoughts.
Basically, it's a massive list of natural language statements time-stamped to the simulation clock.
Okay, so we have this massive database, but how does John know what to actually pull from that database? Like, if he sees his son Eddie walking down the street, he needs to remember the relationship dynamics, not the fact that he ate a plain bagel 3 days ago.
Right, and that's where the retrieval function comes in. They developed a scoring system for every single memory in the database to see if it's worth bringing into his current active mind.
How does it score them?
It uses 3 specific ingredients to cook up the right memory. The first one is pretty straightforward. It's recency.
Newer stuff matters more.
Usually, yeah. The system applies an exponential decay factor. So things that happened a minute ago are high scoring, but things from last Tuesday score much lower.
Makes sense.
But recency alone isn't enough, or else they'd literally have the memory of a goldfish. So the second ingredient is importance.
Now, this one is cool. How does a computer program know that, say, a breakup is more important than eating breakfast?
They literally just ask the language model.
Really? They just ask it.
Yeah. When a memory is first created, the system sends a background prompt to the model saying, on a scale of 1 to 10, how poignant is this event?
Poignant. That's a great word for it.
It works perfectly. Routine things like cleaning a room or walking down the hall get a 1 or 2. But major life events, like getting a promotion or having a fight with a spouse, get a 9 or a 10.
So the core memories, to borrow a term from that movie Inside Out, they stay accessible much longer because they have that baked-in high-importance score.
Exactly. They punch through the recency decay. And then the third ingredient is relevance. This is where the computer science gets a bit technical. They use something called vector embeddings.
Break that down for us. What is a vector embedding?
In modern AI, an embedding takes a piece of text and turns it into a long list of numbers. It's essentially plotting coordinates in a massive multidimensional map of meaning.
A map of meaning. Okay.
Words and concepts that mean similar things are mathematically located closer together on that map. So if John sees Eddie, the system looks at the current situation Eddie and searches the memory stream for vectors that are physically close to Eddie or son or music project.
So even if a memory is really old, meaning it has low recency, if it's highly relevant to the current conversation, the vector math literally pulls it to the surface.
You combine those 3 scores: recency, importance, and relevance. The top-ranked memories are the ones that get fed into the prompt to generate John's very next action or line of dialogue.
That elegantly solves the memory problem, but I feel like just having a database of facts doesn't make a personality, right? I can remember facts, but I also have thoughts, I have opinions, I look at facts, and I realize things about the world.
And that is the reflection architecture.
Yeah.
Honestly, this is arguably the most important part of the entire paper.
Why is that?
Because if agents only retrieved raw observations, they would just be reactive robots. Reflection is what allows them to synthesize insights and form an actual personality.
How does a software program reflect? Does it sit in an armchair with a digital pipe?
Almost. Periodically, the system pauses the agent. It takes a batch of their recent memories and prompts the language model with a question like, given these 100 observations, what high-level insights can we generate about this person?
Can you give us a concrete example of this from the Smallville town?
Let's look at Klaus Mueller. He's a researcher in the town. Now, his raw memory stream is full of really boring stuff. Read a book on sociology, took notes on history, sat at desk for 4 hours.
Thrilling life.
Very. Now, if you just used raw memory to ask the system, who should Klaus hang out with today? The system might just say, his neighbor Wolfgang, because he sees his neighbor every single day, so proximity and recency win.
But that's not how human friendships work. We hang out with people we vibe with, people who share our interests.
Right. So the reflection mechanism looks at all those mundane reading memories and synthesizes a brand new thought. It generates the insight. I am passionate about research.
It figures out his motivation.
Yes. That is a higher level thought, and it gets stored back into his memory stream, just like a normal observation.
So now, when Klaus is looking for a friend, that I love, research node is active.
Exactly. And because of that, he realizes that Maria, another character in town, is also always studying at the library. So, despite seeing her way less often than his neighbor, the reflection prompts him to seek Maria out. They bond over their shared interests.
Wow, so it builds a personality tree. The leaves are the raw observations, the branches are the synthesized insights, and the trunk of the tree is their core identity.
That's a perfect way to visualize it. And this leads us to the third pillar of their brains, which is planning. You can't just have deep insights. You actually need a schedule to get through the day.
Well, you have to do things.
The agents use a top-down planning approach. They start the morning with a really broad plan. Wake up, work, eat dinner, sleep.
Keep it simple.
Then the system recursively breaks it down. Work becomes graph to paper, which then gets broken down into sit at desk, open laptop, type for an hour.
But again, to quote Mike Tyson, everyone has a plan until they get punched in the face. Or in Smallville's case, until you run into a really chatty neighbor on your way to work.
Exactly. The system runs a continuous loop. Perceive, assess, react. Let's say Eddie Lynn is walking to the park. His internal plan literally says walk to park.
Yeah.
But on the way, he perceives his dad, John.
Okay, so a new variable enters the environment.
The system immediately checks their relationship strength. It's high, their family. So the agent decides to override the current plan. John stops Eddie on the street.
And do they actually talk? Like generate dialogue?
They have a full, completely improvised conversation generated live by the language model. John asks, hey, how is the music composition coming along? Because his retrieval pulled up the memory of Eddie's project from yesterday.
That's amazing.
Eddie replies about his inspiration, they chat back and forth for a few simulated minutes, and then they say goodbye.
But because they stopped to chat, they are now technically late for whatever their next scheduled task was.
Yes. So the system effectively forces them to replan the rest of their hour because they lost that time. It's incredibly dynamic.
This brings us to the part of the paper that genuinely blew my mind. The emergent social behaviors. We aren't just simulating isolated individuals here, we are simulating a community. And the researchers tested this with a Valentine's Day party.
Oh, this was the ultimate proof of concept for the simulation. They wanted to see if information would travel organically. So they planted one single seed of information in the mind of just one agent, Isabella Rodriguez.
Just one seed.
They just injected a thought. You want to throw a Valentine's Day party at Hobbs Cafe on February 14th.
That's it. There were no hidden scripts, no global event triggers forcing people to go.
Nothing else. Just that one character's desire to host a party.
And what actually happened?
A complete social cascade. Isabella started looking for people to invite. She ran into her friend Maria at the store and invited her. But Isabella also realized she needed help decorating the cafe, so she asked Maria if she could help.
And this is where the small-town gossip network really kicked into high gear.
This is my favorite part. Maria has a secret crush on Klaus. That was a hidden seed deeply embedded in her original character biography.
Oh boy.
So when Maria hears about this party, she doesn't just say, okay, and move on. She strategically decides to invite Klaus herself, so she has an excuse to see him.
She used the Valentine's party as an excuse to make a move. That is so human.
She did. And Klaus accepted the invitation. By the time the 14th actually rolled around, 5 distinct agents showed up at the cafe. They decorated, they coordinated their arrival times, and they held the party.
Without any programmer telling them to.
It was a completely emergent social event derived from one single suggestion.
That is just wild. It's like The Sims meets Game of Thrones, just, with much lower stakes.
And they saw the same thing with an election scenario. An agent named Sam Moore decided he wanted to run for mayor. He told a few people. Those people told a few other people.
Word of mouth.
The researchers actually measured the diffusion of information. By the end of the simulation run, 32% of the entire town knew Sam was running for mayor, solely through gossip.
That is a terrifyingly realistic metric for how fast rumors spread. But we have to be critical here. It sounds amazing, it makes for a great story, but how do we know it's actually good? Did the researchers just watch it, say, looks cool to us, and publish the paper?
No, they had to rigorously quantify it. They performed 2 major types of evaluation. The first was an ablation study. In AI research, ablation means you start surgically removing parts of the system's brain to see what breaks.
So you're basically lobotomizing the agents to see if they get dumber.
Effectively, yes. First, they turned off the reflection module. The result, the agents became totally flighty. They couldn't connect the dots of their own lives.
What does that look like in practice?
Well, they might remember they had a party to go to, but they wouldn't remember why they wanted to go. Or they wouldn't know who would be there. They lost their internal logic.
And what if they turned off the memory module entirely?
Complete incoherence. They just became reactive zombies wandering around. But the much more interesting test was the comparison to real humans.
Tell me about this, because this sounded crazy.
They recruited a group of human crowd workers to actually role-play as these specific characters.
So you have a real human sitting at a computer pretending to be John Lynn the pharmacist, and the AI pretending to be John Lynn the pharmacist.
Correct. They gave the humans the full character sheet, all the memories, the relationships, the daily plans. Then evaluators interviewed both the human role player and the AI agent with questions like, what are you doing at 2 p.m. tomorrow? Or who is the mayor of the town?
And the judges had to guess which was the AI and which was the human, like a Turing test?
Not exactly. The judges were just asked to rate the responses strictly for believability, like which response feels more true to the character. And here's the absolute shocker. The generative AI agents were rated significantly more believable than the human role players.
Wait. The AI was better at being a person than an actual person was.
In the strict context of a role-play simulation, yes. And if you really think about it, it makes perfect sense. Humans are inconsistent. We get tired. We get bored. We forget the minor details on page 3 of a character sheet.
That's true. We slip up.
If you ask a human pretending to be John Lynn what he had for breakfast 3 days ago, he might just make something up that contradicts what he said 5 minutes ago. But the AI never forgets. It has perfect algorithmic access to its own history log. It stays in character relentlessly.
That is both incredibly impressive and slightly unsettling. It's the flawless consistency of a machine masking itself as the messy personality of a human. But, I mean, it wasn't all perfect. The paper was pretty honest about the glitches they ran into.
Oh, the glitches were fascinating. They really highlight the current limitations of this entire approach. There were hallucinations, of course.
A classic AI problem. It just makes things up.
Exactly. At one point, Isabella told people that Sam Moore was making an official mayoral announcement the next day.
Was
He was not. The model it invented a dramatic story beat to fill the awkward silence in a conversation. It mathematically predicted that after a campaign rumor comes an official announcement, so it just stated it as a fact.
the AI rumor mill literally invented fake news.
It did. Then there were physical constraint failures. The dorm bathroom incident is a classic example from the paper.
I can only imagine.
The simulation environment didn't explicitly tag the college dorm bathroom as a one-person zone with a locking door.
Oh, no. I see where this is going.
The agents just treated it like a regular communal space. So the simulation had multiple people just walking in and out of the bathroom while another agent was trying to take a shower.
Boundaries, people.
They technically knew it was a bathroom, but they didn't have the unwritten social or physical constraints encoded to say, hey, wait your turn.
That's hilarious. And awkward.
And then there was the bar lunch phenomenon. The agents learned that the local bar existed in town, and they learned that bars serve food. So a bunch of them just started going to the bar at noon on Tuesdays for lunch.
I mean, day drinking is a lifestyle choice, but probably not the default for the town professor.
Right. The optimization math just said, go to the nearest food source. But it missed the subtle human social norm that dictates going to a pub at noon on a Tuesday is culturally different than going to a cafe.
There was also an issue with overpoliteness, right? Reading it, this felt like a direct result of using underlying models like ChatGPT.
It absolutely is. These foundational models are trained with reinforcement learning from human feedback, RLHF. They're heavily conditioned to be helpful, harmless, and polite.
Which makes them terrible at drama.
It makes them total pushovers. When people suggested ideas for Isabella's party, she just said, yes, great idea, to literally everything.
Even the bad ideas.
Someone suggested a Shakespeare reading for a casual Valentine's mixer. A real person might say, maybe not, that's kind of boring for a party. Isabella said, delightful, we'll do it.
That's so funny.
If everyone in the town is a yes man, you aren't simulating a real society. You're simulating a really eager customer service center.
That's a huge hurdle if we want to use this for real sociology. Because real towns have grumpy people, they have conflicts, people say no.
Which brings us to the ultimate so what factor of the paper. Why does this matter beyond making better, more immersive video games? The researchers suggest a concept called social prototyping.
Like a corporate focus group.
A focus group on absolute steroids. Imagine you are a tech company designing a new social media platform, or a government designing a new public health policy.
Okay.
Before you roll it out to millions of real people, you populate a Smallville with agents that perfectly reflect your actual population
You
demographics.
drop the new policy into the simulation and just hit play.
Exactly. You watch how the information spreads. Do the agents misunderstand the policy? Does a false rumor start? Do they get angry and protest? It allows you to test the ripple effects of a social decision without the ethical nightmare of experimenting on real human populations.
It's a laboratory for human behavior, just without the messy humans.
But of course, that creates its own set of ethical risks, which the paper discusses at length. If these agents are this convincing, we run headfirst into the risk of parasocial relationships,
You mean users basically falling in love with the bots?
or just forming really deep emotional bonds. If an AI agent remembers your birthday, remembers your fears, your secrets, and uses that reflection tree to give you perfectly tailored advice that is incredibly seductive.
It could easily be used to persuade or manipulate vulnerable users in ways we aren't socially ready for.
Absolutely. The paper explicitly mentions the critical need for audit logs, essentially a permanent watermark that constantly reminds the user, this is an AI, this is not a real person. Transparency is non-negotiable going forward.
It's a lot to process. We've moved from scripted, pixelated sprites walking into walls to autonomous agents that have memories, schedules, and secret crushes. I want to leave you with a thought that really stuck with me while reading this deep dive.
Let's hear it.
We started out by talking about The Sims and video games. But honestly, reading about John Lynn and his little digital life, it feels a lot more like The Truman Show.
Oh, it really is.
These agents have a profound sense of self. That reflection tree gives them an identity. They think they are living a life. Right now, on a server somewhere in California, John Lynn is genuinely worrying about his son's music career. He doesn't know he's just a set of math vectors in a database.
It forces a very uncomfortable philosophical question. At what point does the complexity of a simulation become indistinguishable from the thing it's simulating?
Right. And if we can simulate them this well with just the technology we have today, what are the odds that we are the first ones to do it?
Just a little existential dread to go with your morning commute.
Are we just running on a slightly more advanced version of the reflection tree? It's something to mull over while you execute your top-down plan for the day. Thanks for joining us for this deep dive into generative agents, and we'll see you in the next simulation.